Welcome to the Guardian Group podcast series. The Guardian Group, providing extraordinary solutions to today's exceptional problems.
Hello, podcast fans, wherever you may be. Todd Comeding with the Guardian Group again, along with Rick Murrah. Good afternoon, Rick.
Good afternoon, Todd.
Today we're going to talk about inductance. That's one of the newer things happening in the ET world. I mean, not necessarily brand new, but it's getting more and more where they're adding active coils and inductors, transformers onto circuit boards, and we're going to talk about how that all works. The first thing we want to talk about is when we talk about what is inductance. Inductance is another parameter in electrical circuits, just like capacitance, resistance. And when we get into inductors, we start talking about another, instead of ohms and picofarads and farads, we talk about a new thing called the Henry. That's how the measurement of an inductance is done in a coil or a transformer. I mean, there's a lot of different variants out there, but a coil or a transformer starts out with a bunch of wraps around a type of core, and coils and transformers. Rick's going to talk to you a little bit about that when we talk about coils, and then when we talk about transformers, and there's a lot of different names that you can use when you talk about inductors. So throw you on the spot, Rick, go ahead.
Thank you, Todd. So when we talk about a coil, there's a couple different types of coils. Coils can have this center core to be air, or the coils can have some sort of material in there. Maybe some of us have seen in the past transformers where basically you take a material and you wrap wire around and around and around and around into different windings, and those windings create different voltages or different currents throughout the circuit, and that gives you different voltages across the transformer itself. So you see step up transformers and step down transformers and other types. But when we talk about a circuit board, obviously we're not going to have a transformer built into a circuit board, at least not yet, maybe one day. Right now, on a circuit board, we just have the ability to take air coils and go around in a long trace. So the copper trace could be long or it could be short. So the long trace would go around in a circle just like it does on a winding of a transformer. It goes around and around. It can go through multiple layers, and this can be used for a couple different things. It can be used as a heater. I know a lot of electronics sits outside. I live in Toronto, so it's very cold. So sometimes you just need to heat up the circuit board to make it function properly. So they use it as a heater coil. And sometimes they actually make it into inductance, creating something called a picohenry.
Yeah, very good, Rick. And, to dig in a little bit on that, a little bit more when you're talking inductance, the more turns you put on the core is going to increase the amount of inductance that coil has. And like Rick said, sometimes it's used for heaters, because like if you think about that, like Rick mentioned, cold in Toronto, you have a space heater, which if you look at that thing, it's basically, you look in there and it's a big coil or a series of wires intertwined back and forth, and then when a current goes through there, it heats up. So obviously, it's to the point where there's enough resistance there with the voltage applied to give you enough current to heat up those wires and create the heat from the space heater like you want. Now, we don't want to do that on a circuit board because you know what's going to happen there. But when we start getting, go ahead.
But you're right, Todd. Electronics has to operate at a certain temperature, right? So it has to either be cooled or it has to be heated, and either use an internal device for this or use an external case of some sort, which does the heating and cooling for you. In this case, the coil can be used for cold environments to heat up the circuit board and the electronics to make it function properly. Nobody likes making a phone call and the switch isn't working properly, so the phone doesn't work. Or no one likes not having internet because the switch isn't working.
Exactly. And another thing that happens when we start getting into PCBs, which we're going to talk about now, is that sometimes that they put in, you can actually develop a primary and secondary, in a PCB. We don't see a lot of it yet, but if you have a dielectric in the PCB, so between layers, you have a dielectric, and you can run a trace intertwined between layer 1, layer 2, or maybe if you need more dielectric, layer 1 to layer 3, and you can actually bring that back up and down through the circuit board, creating a winding over that core, and then you can actually intertwine in there a secondary, another trace, that may not have as many loops between the two, and you develop a primary and secondary. So when you apply a voltage, that you can actually get some characteristics of a transformer. In this case, they usually use it for waveform shaping, and that's what we're going to start talking about, why testing inductance on a PCB is more important now than just using a standard continuity test to make sure the traces of these inductors are working. But once you get those primary and secondaries to work together, you add a capacitive component to it, and you can actually do some waveform shaping. It all comes down to, with coils or transformers, they change the relationship between how voltage and current work together. When what they call the reactance, when you have capacitive resistance and inductance in there, you get talking about what's called reactance. And when your reactance is equal capacitive to inductive, you have basically resonance of that circuit, and whatever power or voltage you apply is fully reflected through that device and on down the line. But when you have a reactance, either inductive or capacitive, your voltage signal will either lead or lag, depending whether it's inductive or whether it's capacitive. So when you're waveform shaping for definitely high-speed circuits, this becomes extremely important to make sure that these devices are working as they are designed. And if we don't check for this type of thing, when we're doing testing, then it could have a adverse effect on the final performance of the intended circuit, even though, quote unquote, the ET level part of it with opens and shorts is
So Todd,
still passing. Go ahead, Rick. I was going to let you start talking about testing inductors.
what about reliability? Is there a difference? Because I know you and I both ran services before for the PCB industry where we've done AOI of the coils and we've done inductance of the coils. Which would be more reliable in your mind?
Well, I mean, I think they both play hand in hand now with the equipment that we have available for doing AVI or AOI. When you're actually looking at the pixels, I mean, on a heater trace or delay trace, when you're on just one layer of the board, I mean, the pixel rasterization of an AOI can be fairly accurate, looking for, shorts in the trace, or maybe dish down or smaller, trace anomalies. But, that can't catch everything. I mean, when we really want to look at it, we definitely need to look at the signature that's coming out of the designed circuit, I think. And so I think reliability wise, I mean, your AOI can probably give you a pretty gross analysis of that type of scenario. But when you get down into, especially in microwave technology stuff, where you're designing in capacitance and inductance, that component of reactance is extremely crucial in higher frequency circuits. So I really think we need to get into the inductive actual test rather than just relying on standard ET, open shorts, and AOI, even though those are valuable tools.
Okay, so what you're saying, Todd, is basically it's better off to make sure that it's done electrically than it is, or a mixture of both.
It all depends on, the availability of what your customer has. I would recommend, based on technology today, especially where we're going with microchips and a lot of regenerating the activity here in the US, we want to make sure that our quality is as high as it can be. And I really think we need to look at the electrical signature analysis of inductive circuits, just like we do with resistive components and capacitive, because these have an effect on today's circuits. So I would rather in my opinion, see a electrical validation of a buried inductance in a PCB.
Thank you for that, Todd. I tend to agree with you. It's better to put some sort of electrical current through there and do a proper measurement. And there's a lot of handheld devices called LCR meters that do a similar job as what we have, where an LCR basically just means you're measuring impedance, capacitance, and resistance. And you know what, Todd? This is what we do with our flying probe lineup, where we have it all set up to measure all this in a simple one test. So
But
when we do it,
when we do this, is this how we use the same kind of premise that we do with buried capacitance and buried resistance? Have we taken that to another level with inductance?
so when we wrote the code for making the test, we actually do everything all simultaneously with the same contact. When we do capacitance and resistors, excuse me, Todd, they are done with the same time, but they're done one by one. In this particular one, in theory, we're doing 3 tests in one hit. Right? We're doing the inductance, capacitance, and resistance. And of course, this type of test, because the coils are small and the leads of the copper wire is long, we need to see small changes in the measurement. So when we talk resistive or inductance, Henry, we're talking micro. So we have to ensure that we have like 4-wire Kelvins probes on there. So the 4-wire Kelvin, they're making double contact on the pads to ensure that the meter readings are very precise.
Absolutely. I know that we've seen some, active type components where we've been asked to test, the actual coil. We have the PCB, and then we also have, there's a coil where they basically give you the little device that's either mounted to the board already. I think in one of our service centers, we've done some activity with this, which we actually were testing the device after it was, I don't know how they laminated or put the coil together, but we're actually looking for some specific responses out of it that a standard electrical opens and shorts test wouldn't do.
That's correct, Todd. Very nice.
So when we talking about inductors, I got ahead of myself. We talked about turns earlier. So you have if you have turns around a primary turns around a form, whether it's air or ferrite or toroid, that combination there, the core permeability against the turns gives you what you're going to get your inductance in henries. When you have just a standard coil, that's what it's going to be. It's going to be a delay trace. You can use it for one thing they do in radio and television type stuff. In antennas, they might use a loading coil, which is basically a wind of wire around a form. A lot of times it could be an air core. And what they do is they might be in a base that's a little bit compromised and they need, to have a longer transmission line. And so they do a loading coil, which would they take the turns around the coil, which basically shortens the amount of distance necessary to get the desired result. And so you can see some of this sometimes now, even in a PCB, if they have a transmission line or something in a PCB that needs to be a certain length, but the PCB is maybe only like 3 inches long or 4 inches long, they can do something like this example that we have here on the screen now, basically where you just have a primary, but you have a certain amount of turns, and that allows that transmission line to get longer, even based on your short amount of space. But then we also get into what we call inductors with primaries and secondaries, and that's why that's important to test for the inductance, as Rick and I have been talking about, because we have a lot more turns. We still have the core, but we have more turns maybe on the primary and the secondary. In our new example on the screen, we have now the actual transformer coil where we have a primary of 18 turns, and we have a secondary of 1 turn. So we're doing something which we call a step down of the circuit. And this could be maybe an attenuation circuit for some type of high-speed frequency. And the other thing they do, we didn't mention earlier, one thing about coils is when they're inductively coupled between the primary and secondary, which means they don't physically touch each other. And what that allows for also is a lot of isolation. And we didn't talk too much about that. That's another reason why they use a lot of coils and transformers, is that they can take out parasitic components across the inductive coupled transformers. So here they might be stepping down or attenuating something, but you're also isolating, which means, if you're running an AC circuit, it'll couple AC but block DC, so you'll get that noise component out. And then you can actually add some capacitance in these and cause some filtering, whether it might be a band stop or a band pass, or you have some frequencies you want to be held not going past this device, where you might only want to pass a higher frequency or lower frequency. A combination of the inductor and a capacitor will allow that to happen. So I'm not trying to get too deep in that, Rick, but that's one of the significant things about why we want to test these things, and why they have why the differences in these things can be so grave as far as the performance of the circuit. So why we test them over standard ET, Rick, I'll let you kind of go over a little bit of this chart here when we talk about resistance versus inductance and what can be the pitfalls if you just wanted to do a standard, maybe just you did AOI and then you just doing opens and shorts check.
Okay, Todd. So when we're just doing standard ET, I think in my mind it's straightforward, but I'll just explain a little bit about it. So if you have a coil and go around in a circle, especially if you're on the same layer, what happens if you have a short in the coil? Standard ET, you're not going to be able to detect that short. And because the trace is so long, probably not going to be able to detect any kind of difference in resistance, because it may be higher than whatever the minimum resistance you are testing that PCB for. So you can miss the short, and it can be different resistance. So standard ET, you will have to either on that particular net increase the standard resistance, or maybe okay, but it just becomes a potential liability because you don't know what's there. So in order to make it more reliable, we strongly recommend that you do a full coil test on it. And in the coil test, you can set up your microhenry range, what kind of range you want, what frequency you want to have it done at, what kind of milliohm range you want to have for the resistance, and what kind of tolerance. So when you're doing the test, you're getting the whole portfolio here. We're going to tell, if I want 200 microhenries and I want to do it at 16 kilohertz, and I want to have plus or minus 1% or plus or minus 2% on that measurement, you can do that. And the same with your resistance. If you are measuring in the range of 2.7 milliohms, and you can set a plus or minus tolerance on that value as well, and it either comes up with a pass or a fail. So in our setup, we can pass the inductance. It doesn't happen very often, but you can pass the inductance and fail the resistance. It's possible to do that. So if you want to be reliable and ensure that when you send it to the assembly house and they build the boards and it works properly, do the inductance test when it's in bare board form. This way you know for sure the coil is going to operate, the inductance is going to operate the way that you want it to within the design that you've laid out in the PCB board.
Absolutely. I can't, stress the same thing enough. I mean, looking at your example here where we're talking in inductance in the first example of L1 to L2, 220 microhenry, frequency at 16 kilohertz. Well, what happens, as I talked kind of lengthy there about coils and caps and reactance, if something happens in that resistive R1 to R2 resistance, you're going to change through inductance. And what's going to happen is at your 16 kilohertz, you're not going to be getting the response that you're looking for because you have changed the resistance. And if you get into, transmission line theories and stuff like that, when you're talking resistance, inductance, and capacitance, they have this nice funky chart called a Smith chart where you can actually chart the reactance, whether it be inductance or capacitance. And when you're moving circuit power down lines, you have what you call your VSWR, or reflected power. So if the circuit isn't doing what it's supposed to be doing based on maybe it was a short and change these parameters, you're not getting the response down the line that maybe in a microprocessor is expecting a certain frequency and timing. And if something goes wrong here, that circuit is not going to operate. Now, it's something you're not going to find with a standard opens and shorts test. So I can't stress enough, like Rick said, why we really need to check inductance for real on the bare board before we go on and add, all the expensive components. So what did we talk about today? In conclusion, we reviewed what induction is. It's basically a change of the relationship between current and voltage using coils and primaries and secondaries. We talked about coils and transformers, what a single turn coil is versus a primary and secondary transformer waveform shaping type device, and we understand what turns are around the coils and why we need to test it in the bare form or in the inductive arena rather than standard opens and shorts. So I think we covered quite a bit there. Rick, do you have anything to add?
Yeah, we covered a lot, Todd. I hope that it was a little bit informative for people when they listen to our podcast. I don't really want to add anything else. I think you summarized it very, very appropriately.
I know that we kind of get into some deep stuff on this when we get into, more than the standard ET that we all know and love, the opens and shorts. But, the industry is pushing us into, building these type of higher type that used to be always discrete components that required bench tests and LCR meters, like Rick mentioned. And now technology's got it to the point where we can actually get this stuff inside the board. So, what the next phase of that is being able to test it using our standard our ET equipment with a couple of little changes here and there in how the machine might be a little bit different, upgraded after it comes out of the box, but we still can do it. We're talking, we can do induction, we can do capacitance, resistance, impedance checking, 4-wire Kelvin, high pot. We're getting all this off the bench now back onto the machine. So number one, it increases the throughput time of your, or decreases, I should say, your throughput time of your work through the ET process, because you're not having to go to the bench all the time. You can get it all done at one time. So we're increasing your velocity while maintaining high integrity, and also we're doing this automatically. So we take that, every once in a while, that human interaction that, we're not perfect, that sometimes can misplace a board here and there. So, the more automation you can get to it, the better off we're going to be at the end. So I digress. But anyway, I want to thank you all for joining us today, talking about inductance. And if you have more questions, or if we got too deep there, you can always send Rick and I a line at info@guardian.com. That's info@gardien.com, or visit our website, www.guardian.com, and look at your favorite libraries of podcasts, where our library is now getting up and going, where you can look at this, see this one and our others, as well as be on the lookout for our videos on YouTube. So with that, Todd Coleman with the Guardian Group, and we'll see you all on our next podcast.